Let me just finish up writing the date. This is 2025. That the name of it basically explains the whole premise. So it is valence shell, that's VS, valence shell, and then EP, electron pair, and then R stands for repulsion. So basically that's what the VSEPR, VSEPR, stands for. It's valence shell electron pair repulsion, which is a whole mouthful, which is why we created an acronym for it. But it basically outlines the same thing. So this is a very good model for predicting the shape a molecule will be in, and especially for these non-metal center atoms. Even though it does work for metals, it is really good for non-metals. But so if you get a metal, it still works, but it's not as there's more exceptions when they're metals. But the metals still work mostly. Okay, so VSEPR builds on the Lewis diagrams that we were doing earlier. So we're going to do a lot of practice with Lewis diagrams in today's lesson. Diagram. And basically to describe the geometry in the molecule. So basically, what kind of shape in space does this thing take up? Because the shape it takes up in space affects how it reacts with other things. So if you know what shape something is, you can predict other properties about it, what kind of reactions it could be involved in. The simple premise that basically describes this whole arrangement is electrons repel each other. So when electrons don't want to be anywhere near other electrons, and that basically dictates the space. So molecules have an arrangement that minimizes the repulsion. So once we get these elements, these atoms together, they arrange themselves to minimize all the bumping into each other they possibly can. So, and this is, they repel in both bonding pairs and lone pairs. So both of these repel each other, because in bonds, there's electrons in bonds. That's what bonds are. So the bonding pairs and the lone pairs both repel each other. And there are exceptions to this, and we're going to get more complicated into the exceptions of this in later chemistry. Today, we're going to go based on these basic, simple shapes, and they always work, because those are the examples I'm going to choose. Spent a lot of time choosing examples that didn't have weird exceptions that you would need more chemistry to understand why those exceptions are true. But for now, this will all work. So this is a very good basis for predictions. Predicting, I guess, in the right sentence grammatical structure, predicting 3D structures. Okay. So the next thing we're going to do here is basically just going to go through each of the shapes, and each of the shapes have a name. So slide down here, and we'll just look at the different shapes. So the first column is groups around the center. So we have a center plus how many extras. And so when we have a center plus 2 extras, it looks like this. We have a center atom here, and there's one on each side. And it makes this straight line shape, and we creatively call this linear. So this is the linear molecule shape. Basically, this atom hangs out as far away from this atom as it possibly can. My favorite example is CO2 is this example. So I can draw it like this. I'm going to draw the shape because it's pretty easy. And just blast through the Lewis's. I've told you guys how to do this Lewis by now. You've probably almost remembered it. So this is the Lewis for carbon dioxide, and this is what shape it makes. When we add 3 atoms around, they arrange themselves like a triangle, and so the angles between each of them is 120 degrees. We call this trigonal plane. Basically, it's a triangle that's flat. That's what we mean. Trigonal plane means flat triangle. But we got to be all sciencey and fancy about it. So we can't just say flat triangle, we say trigonal plane. So, and plane in this case has nothing to do with aircraft, it means flat, like a two-dimensional flat surface. My example for this one is boron trichloride. So I'm just going to write, let's do it properly. B, in the middle, and there's 3 bonds on each side, and there's a chlorine on each one. Boron trichloride. What's funny? I mean, a lot of these are going to be really fun to say. Some of these are going to get more and more complicated because we're basically just adding more and more elements around the corner. So as we slide down, we're now to 4 elements around the outside. We call this shape a tetrahedron. Our 4-sided shape. Same shape as a dice. The common one is methane. It's going to starting to get harder to draw here. So we draw this shape, and if you remember from organic chemistry, we kind of draw shapes like this. And so this kind of shows the like 3-dimensional shape, kind of. You can kind of see how this front one here matches out this one kind of coming out front here, and then this one kind of going out to the back, this one kind of goes out to the back. So the computer-generated 3D image is significantly better than my stick drawing of it. Which is why I included all those pictures, and I didn't make you draw any of these. I included all of these in the lesson, because, honestly, gross. And I want you to understand what they are. The next shape is getting really big. We're getting 5 things around our central atom. Boringly, we're going to call this one... No, actually, never mind. This one's a cool name. This is called... Oops, pen back on. Trigonal bipyramid. So this is a trigonal bipyramid. It doesn't really look like a trigonal bipyramid in the picture, but if you like shade in all the sides and connect it, it's like a triangle pyramid on top of another triangle pyramid. It's kind of the shape. Let's see if I can do it really quickly. I'm going to erase this because it's going to look messy if I keep this on the notes. But if I draw lines like this between each of the atoms, you can kind of start seeing where the triangle stuff comes from. So now you can kind of see where that double triangles come from. I'm going to erase it now because it's going to be messy, but you can kind of see where the triangle on top of a triangle comes from in this particular arrangement. So let me just erase all that before it gets really messy in the notes. I want to leave that there. Okay, my example for this one is, I'm not going to draw it. It's going to get out of hand. I'd let the 3D picture do it properly. I'm just going to say PF5. I'm not going to get into the drawing of it with the stick drawing. It's not terribly important. We're just trying to identify these shapes at this time. And if you wanted to draw it, it kind of looks like this, right? You would just put the P in the middle, the phosphorus goes in the middle, and the fluorines go on each side. That's where they go. Okay, the 6-sided shape one is called an octahedron. Which sounds weird, right? Why is the 6-shaped an octahedron? It's because there's 8 faces on this shape if you draw it in. So this is SF6, or sulfur hexafluoride, which is one of my favorite compounds. It's a dense gas that's not poisonous, and so it can make your voice deeper, the opposite of helium. I still have yet to actually physically get any, because it's very expensive and only comes in industrial-sized containers, because it's used for refrigeration or something fancy. But I can't get any myself, which is disappointing. 7 is getting really out of pocket. It's pentagonal bipyramid. Pentagonal bipyramid. Basically, a pyramid on top of another pyramid, but each of the pyramid has a base of 5.
Do we have to remember these names?
It's pretty obvious which one it is. A little, yeah. Yeah, pentagonal bipyramid. 5-sided double pyramid. What? It's not that obvious? It's not a double, it's a double pentagonal pyramid? But yeah. I'll say it properly. This one's fun. This one actually has a metal one. It's the only one I could find that does this. As they get bigger and bigger, they get more and more obscure. So So zirconium heptafluoride is getting really out of pocket. Zirconium heptafluoride there. I'm not going to try to draw that. It's the same as the picture there. And the last one is my personal favorite. This is like a center, and there's two squares on each side. And so this is called a square antiprism. Prism is like a three-dimensional shape, and it's square on the top, square on the bottom, and it's antiprism because the point's in the middle, not like these two where the points are on the outsides. Here, the point of the pyramid is on the inside. I think so. And also cool is like it's this one lines up with the space, and so they're not like right on top of each other. They're twisted a bit to try to... Remember, the whole point of these things is that each of these atoms wants to be as far away from the other atoms as possible and still have 8 of them together. What we can do with this thing is really fight a xenon together. So if I turn this back on, we get xenon octafluoride. And you might think to yourself, why does xenon do anything? Xenon's a noble gas. But if we put enough fluorine beside xenon, some will stick, basically. So if we put xenon and fluorine together, fluorine is electronegative enough to grab on to xenon's extra electrons, basically. Xenon is huge. It has 54 electrons. And so if you put fluorine super electronegative, like a super strong magnet, it's going to attack anything around. So we can actually stick fluorines to xenon. It doesn't stick to like neon or helium. They're too small. But it does stick to xenon, which is pretty big. Okay, so those are just basically each of the shapes that we have. And now we're going to edit those shapes and make new shapes. Because basically we're going to add lone pairs to this. So we're going to add lone pairs. So when we add lone pairs, they take the place of a bonding pair. In the geometry, basically we'll replace one of the circles in the above pictures with an empty space like an electron pair. So that it will change the shape you actually see. But each of the shapes has the same base pair. So lone pairs actually have more repulsion. Oops. More repulsion than bonding pairs. So arrangements minimize this repulsion above bonding pairs. Minimize the repulsion. Whoops. Just really had to jam that in there. Above the bonding pairs. So basically, two lone pair chunks want to stay further away than bonding chunks. So when we're picking where to go with the bonding and the lone pairs, where should they go? You want to keep the lone pairs as far apart as you can. That's generally the goal. Okay, so the first chunk that I have here is just the same as it is above when we have no lone pairs. So it's just a basis. So I wanted the chart to stay somewhat the same. So we're just kind of lining them up right now. So I'll slide this up here. So these are the first 6. We don't get into the big ones with lone pairs because they don't really exist with lone pairs. The small ones, this is just going to be all the same words that we had above. This is trigonal plane. This is a tetrahedron. This is a trigonal bipyramid. And octahedron. Okay. So those are just our starting points there. Let me shrink this up so it all fits nicely on the screen there. Okay. So then...
Wait, is this Folger's books?
Yes, it is. We're going to take one of the top pictures, take one of the atoms away, and replace it with a lone pair, with the dots. So basically we're looking at this kind of pair here, and we're going to take this atom off and replace it with the pair. So that's the kind of analogy we're working with here. And so we have the same basic shape, but with one of the lone pairs gone. So we take one of the atoms off, replace it with the lone pair, and we get a different shape. And when we're naming the shape, we just name the shape based on the atoms that are left. So this shape kind of does this like slanty one, and we creatively call it bent. That is a bent molecule. I know, right? I'm really creative here. That's the official chemical phrase for this shape is bent. So this is a bent molecule. And then we have our fourth group one. We look and say, okay, we'll take the top one off of this one and replace it with a lone pair. And then we can see we have this 3 tripod kind of shape, and it's a trigonal pyramid. Not a bipyramid because it's just one of them. So just trigonal pyramid. Because just one. So trigonal 1 pyramid. So just one 3-sided pyramid. Next ones are getting weirder, and I'm just going to show you the shape. We could get into the math, why the shape is this way it goes. Basically, which one of these do we take off has to do with where the extra space is. I'm not going to get into that. We take off this one, the one on the side, and we're left with this whole shape. This one's more fun to say. This is the real chemical name for this. This is called seesaw. That's true. Because we kind of like have this like straight line here with 2 legs. It's kind of like a seesaw. So we've got the straight bit and like the little legs off the side. I mean, it would make more sense if I turned it sideways, but that's the way the image came out of the book. So that's the one we're going to do. So this one is a seesaw, and the last one we're taking off, it doesn't really matter because it's 3-dimensional space, whether we take off the top one or the bottom one, but we're left with just basically a regular, everyday pyramid. And we call it square because that's more accurate. Square pyramid. Just like the Egypt ones, a straight square pyramid. Square base, 4 on the bottom, 1 up top. That minimizes our electron repulsion. I only included one more for 2 lone pairs because they get really out of hand past this, but we're just going to kind of stop here because those are the ones that we're actually going to encounter. They're pretty common shapes. We don't usually go too far more complicated than this. So the next page ones are if we take 2 elements off. So we take 2 atoms off, replace both of those with lone pairs, and we get the shape that's left. This corresponds directly up above. It's kind of hard when we shift pages, but we basically have this bent molecule again. Now the difference between, let's see if you guys can notice. What's the difference between this bent one and the last bent one? Yeah, the angle between the 2 is different because 2 lone pairs are going to squeeze those 2 atoms together more than if there was just 1 lone pair squeezing them together, kind of pushing on the side. So this one only has 109 degrees. Well, actually, slightly less because it's squeezing. But if you can notice, all the angles kind of match. All right, if we take 2 off of the 5 shape, we can get this T shape. So this is called the T shape. So again, very creatively, we have T shape here. We take 2 off the base of the trigonal bipyramid, and so we're left with like a planar T shape here. And the last one, when we take them off the 6 shape one, we take the top points off my octahedron, and we get a square plane. Square plane. Yeah, just square, right? But specifically, square in a plane. Not square on a diagonal, not square in a rhombus, not square in anything else. Square in a flat plane. So a perfectly flat plane. Okay, so basically now we're going to use basically these rules and our Lewis diagrams to predict shapes. That's our job for the next little one. Okay, first example, a nitrite. So I want to go through all the Lewis stuff. Because specifically, if you forgot last week's Lewis diagram stuff, how do we draw the right number of bonds and electrons and all of this stuff? So we're going to I'm going to remind you of the NaSl stuff, right? NaSl little maneuver here. And we're going to try to do this. Now, once you get used to these, you're going to get very comfortable with them. You can start predicting these diagrams a bit better. Okay, So how many electrons does these three atoms want? How many does our nitrogen want to be full? 8 to be full. Because we're doing N first. N first is how much we want. So I want 8 there, 8 there, 8 there. So 3 eighths, that's a total of 24. So my N number in this case is 24. That still doesn't matter yet. That matters in the next line. So in the next line, we care about how many electrons are each of these coming with. So how many electrons do we have available to move around here? So the nitrogen comes with 5. So I'm going to show you guys this. We got lots of room in this little spot here. So we've got a long page here, so I might as well write all the things. So we've got 5 plus 6 plus 6, 5 from nitrogen, 6 from each oxygen, and 1 from the minus charge. So we have that extra 1 coming from that -1 charge on this nitrite ion. So all of that together gives me how many? 18. So 18 is the number of electrons we have to put into the diagram. So what does the S1 mean again? What does the S stand for, Bo? Oh, we just look at full octets for each of the elements. So each of them are group 2, row 2 P elements, so they're going to all want 8. The exceptions are hydrogen wants 2, and beryllium wants 4, and boron wants 6. But otherwise, everything else is 8. So we're going with that. So that's where the 24 came from. So what does the S stand for? Anyone remember what S stand for? Shared. So this is our how many bonds one. So we do a subtraction. This is 24 minus 18, which is 6. So that means what? They share 6 total. So that's 3 bonds. I'm doing this the whole long way first. We're going to zoom through this part later, but I figured we should go through this part as a memory first. So 3 bonds. And then we do the subtraction again. It's 18 minus 6 for how many lone pairs are left. What is 18 minus 6? It's 12. So there's 12 electrons or 6 lone pairs. I'll just put LP there because I'm lazy. So we know we're going to have nitrogen and 2 oxygens. Which one should go in the middle? Nitrogen in the middle. So we're just going to go straight nitrogen in the middle, and we know we have at least a bond on each side for like this. We know it's going to look a little bit like this. We don't need to worry about shapes yet because we're just doing the Lewis. We don't really care about shapes right now. How many bonds are we short right now? Just 1 short. I need 3. I've given 2. So we got to put up, whoops, that was the eraser button. So one of them gets a double bond. This will be a resonance structure, but we'll skip that for now for ease. It's either or, so it's like a 1.5 bond, but that won't change the shape. So it doesn't matter for shape. How many electrons should I add? Figure out how many electrons to put in. So we need 6 pairs, right? 6 pairs are left over. I know I can put a pair here. I know I can put a pair there. Because we're trying to fill up each element's octet rule. So now oxygen sees 8. I know I can put 2 above the nitrogen because that gives the nitrogen 8. And how many left do I have? I should have 3 more pairs. Can I put them all on the oxygen here? Yeah, I can put them all there. That means, if I'm counting, I've got 8 around here, 8 around here, 8 around here. So this is going to give me my, what's it called? My correct Lewis diagram. So this is the correct Lewis diagram for all the electron pairs. All the bonds are all there. So now we've got to figure out how many things are around my center atom, right? How many groups are there around the center atom? 3. There are 3 groups. We have 1 group for the lone pair. We have 1 group for this double bond. And we have 1 group for this single bond. There are 3 groups around this element. So that's how we're going to figure out this shape now. So this shape is based on a 3-group base. So if we flip back to the page that has the 3 groups on it, that's our first column, right? So we're looking at 3 groups with 1 lone pair. What shape has 3 groups? I'm going to write it here, 3 groups and 1 lone pair. So what shape has 3 groups and 1 lone pair? It is just 1 page back. That one there. Back to this page. So this is going to be a bent. That's it. And you can draw a quick, that's all we're going to work with. That bent. It's a bent molecule. Very exciting. Ooh, okay. So next one, ammonia. Oh, I wrote that wrong. Anyone going to tell me what I did wrong here? Yeah, I got too many hydrogens. Ammonia doesn't have 4 hydrogens. Ammonia has 3 hydrogens. So let's cross that out. None of that nonsense. That's a 3. Sorry about that. Let's make sure we all get that mistake fixed. Ammonia only has 3 hydrogens. So let's do our Lewis diagram of ammonia. It's easier. The nitrate one was probably the hardest. So we can do NaSl, but you probably already know what the Lewis diagram for ammonia is. We did it before. Maybe I'll just show you the Lewis diagram here, because I feel like I've done it 800 times now. Right? We've seen the Lewis diagram of ammonia a few times. So let's just draw the Lewis diagram. If you want, I can talk through how it comes about later, but so I don't talk for 1,000 hours, we'll just get to this one. Okay, how many groups does it have? That's what we're looking for. How many groups? What column should I look in? This has 4 groups. So remember, when we're talking groups, we count the pairs. So when we're doing groups, we count pairs. So this has 4 groups. 4 groups, how many lone pairs are there? One lone pair. So what shape does it come? So we're looking at group 4, so we're probably back a page. So 4 groups, 1 lone pair. We flip back here. This looks like this thing, right? We're in the 4 groups, 1 lone pair. We're at this shape. So it's a trigonal pyramid shape. So back to the page here. We're going to write down trigonal pyramid. So it's kind of, let's see if I can draw it. That's not terrible, but it's okay. The 3D drawing is there, so you can see it. Okay. That's not bad. Any other questions on these ones? Okay, the next one's nice and easy too. We already know the answer to this one, right? What shape is water? Water is bent. We know water's bent. I've said water is bent 100 times. This is why water is bent. So we're going to draw the Lewis diagram of water, right? Put the O in the middle, put an H on one side, put an H on the other side, and we have a lone pair here, and we have a lone pair here. So we have 2 lone pairs on our oxygen, and no lone pairs on hydrogen. Everything is happy. This is just the Lewis diagram. And so we can say, how many groups are there on this hydrogen? 4 groups. Sorry, on the water. On the water, fair. On the water, there's 4. On this oxygen, there's 1, 2, 3, 4 groups on this particular water group. So this is a water, has 4 groups. How many lone pairs? 2 lone pairs. And so this is a bent, whoops, sorry about that, slide it around. There. This is a bent shape. And so this is going to be a tighter bent shape than the other one. Oops. To be very pedantic, I'm not going to quiz you on this, but it's going to be like 100 and, this one has 115 degrees. And this is just because I looked this up. It's not because I'm expecting you to know this. This one is 104.5 degrees, right? So the water one is bent tighter than the nitrite. So they're both bent shapes, but water is bent into a tighter angle than the nitrite. And I would maybe ask you which one's bent tighter. You could probably do that. Numbers, no, that's experimentally determined, doing a whole bunch of stuff. But yeah, you would expect the water to be more bent because it's got more electrons, right? It's got these like lone pairs hanging out here and here, causing a whole bunch of electron repulsion, pushing everything away. So it's got that whole electron chunk of it there. So let's put them in there. Let's just draw dots. Sometimes they're drawn like clouds. That's a really ugly drawing. I'm very sorry, but it's kind of got the point here. And this one would have like electrons up here in this cloud up here. So only one of them is pushing it down there, and these ones are, yeah, it's messy, but it's fine. All right, so we know we've got, how many electrons do we have? Basically, let's just start with halves. How many electrons are there in this whole molecule? How many does sulfur come with? Sulfur comes with 6. So the 6th one across, sodium, magnesium, aluminum, silicon, phosphorus, sulfur is the 6th one across. And each fluorine comes with 7. So I'm just going to write all oh, that's gross. Next one, we're going to do 7, 7, 7. So that's 28 plus 6 is 34. Okay, so we got that. There's 34 electrons to play with. We know that's true. So we know we're going to have a sulfur, and we're going to have, let's just do it this way. We know there's at least this going on. So we've got F, 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 and F up here. I got that really close. Let's see if I can slide that down for my own drawing here. Aw. It doesn't make sense. It doesn't follow the rules perfectly, because that's not how any life really works. Okay, so the next thing we're going to do is we're going to start, how many electrons have we used up already? We've used up 2, 4, 6, 8. So we've used up 8. And now we can put all the electrons around each of the fluorines, because we know we're going to fill each fluorines with 6 lone pair, or like with all the 6 electrons, right? We know each of the fluorines is going to look with a big cloud of dots, right? It wants all the electrons around it. So this is the basically way we do this one. So we got all of the fluorines have this many. Okay, so now that all the fluorines are full of electrons, is that all the electrons used up? No? Is not all the electrons used up? How many electrons have I used up? I've got, you start counting, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So how many am I short? I'm 2 short. Where can they go? Can I put them on fluorine? No, fluorines are all full. They can't have anything. Can the sulfur take on extra ones? Yes. It's full, but I have the electrons. They've got to go somewhere. And so they do go in here. So we actually have a lone pair on my sulfur. Sulfur is in that 3rd row. It can take extra in the expanded octet. So we have a hypervalent sulfur here. We can take that extra one and go there. So it shouldn't start with that. We started with what we had. We put all the electrons in there, and we have that extra dots on sulfur. Doing these lots of electron ones, we want to start with counting the electrons. So, total electrons. Each of these, how many electrons are in this compound? I got bromine and fluorines together. How many does a bromine come with? How many does fluorine come with? 7. Right? They're both in column 17, so they all come with 7. So that's a total of 28 electrons, right? You guys really probably didn't need the calculators out during that one, but 4 7s, right? So I'm going to draw the shape as I think it looks, and then see if I've used up all the electrons, and then choose where all the extra electrons go after. So we start with a Br in the middle, and I put a fluorine on each side. That's where I'm starting with. Just starting here. I know I have this, and I know the fluorines are going to fill up their outsides. So we can start throwing electrons around the outside to try to fill them up. Fluorines all the way around a fluorine. Okay, so we're going through, each of the fluorines gets filled up, so each of those sees our fancy octet. And then we just got to put all the extra ones on the bromine. And bromine normally only wants 8, but bromine is in row 4, so it can definitely take them if it has to. So, how many electrons have I used up? Let me just go through the count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, right? 24 are used up. I'm 4 short of where I need to be, so that's 2 lone pairs left. So I got to put 2 lone pairs on the bromine. So it's a bit messy. Bromine has way too many electrons, but now I've actually used up all the electrons. Okay, how many groups? You guys have learning the pattern yet? How many groups on this lovely molecule, I guess? There are 5 groups, right? So this is 5 groups, right? 3 bonds, 2 lone pairs, 5 groups, and 2 lone pairs. So then we go to the table and look up what has 5 groups and 2 lone pairs. This is the T-shaped one. So this is a T-shaped molecule. So 2 of the octagon is gone. 2 of the trigonal bipyramid one is gone. That's the way it goes. So this is a T-shaped one. I'm not going to draw the T-shaped one. I copied the T-shaped ones because I just have them answered. Okay. I can count. Because iodine has 7, iodine has 7, iodine has 7, negative charge. Oh, it's the 7th across. Iodine is 53, so it's the 7th across. It's column 17. So it comes with 7 valence electrons. It's the same as fluorine and chlorine and bromine and iodine. They're all the same. I know there's a whole bunch of elements in the middle, but they don't count.
So like 7 from what?
The D column in the middle between 3 and 12 don't count. Because they are stable. They're like a core set. So when we're doing the arrow diagrams, those are set to be in the middle. They will never be in bonding. A full D shell is full. It doesn't get messed with. Okay, so what we're going to do here is, we know we're basically going to let's just draw this like this. Oh, geez, that's not how I draw a letter I. Okay, so we're going to have to start this. This is the minimum set. And so we're going to see if we get lone pairs going in here. So let's fill up the outside iodines, because those are going to be the first ones to fill up. We're going to fill up those like this. It's a tough day. Oh, well. Okay. We know we're there. We got to figure out how many we have left. They're all going into the middle. Okay. I have used up, let me count through, 2, 4, 6, 8, 10, 12, 14, 16. I have 6 left. Okay. 6 left. That's 3 pairs. 1, 2, 3, 4, 5, 6. This should be 22 now.
Yeah. Oh, yeah.
Is that 22 now?
Yeah.
Okay, great.
That's only having those only.
No, that's 3 lone pairs. It's not one of the options. But how is this shape going to be? It's going to be a line. This is a linear shape. It's a linear shape. This is a straight line.